I'm doing just a general presentation today about my current thoughts about the mesh. I've been doing the Twitter for 8 years, and it was a big part of how we grew. And I've tried to get other people to get involved with Twitter, but yeah, it ended up being just me mostly for the 8 years. But I'm just disgusted with what's going on there at the moment, so I got off Twitter. And Toby has volunteered to take over our Twitter account. But the exciting thing is we've set up a Mastodon server. So Mastodon's kind of the open source alternative, and it's been growing pretty quick. We're getting about four or five new members a day. And yeah, you can all join. There's a URL there, mastodon.nycmesh.net. We're limiting it to only mesh people at the moment. It might stay that way, because it's you get into moderation problems if you just let anyone join. So as long as it's just mesh people, we should be fine. So I took a 2-week holiday this year. It was my longest holiday in a long time, and I went to Spain. And a big part of our inspiration for doing NYC Mesh was this network in Spain, GUIFI. And we copied a lot of their things, especially the Commons license and the way they were doing wireless networking at the time. So while I was there, I visited Ramon Roca that started GUIFI, and we were hanging out and chatting very intensely for one evening there about all the problems with networks and the history of GUIFI and everything. They've got 37,750 nodes, which is almost exactly 30 times the size of ours. It's a pretty huge network. It's the second biggest. Like there's basically a monopoly, Telefonica there, and GUIFI is the only alternative in the country. And the thing I didn't appreciate until much later was that Catalonia, where GUIFI is based, is fiercely independent and has a really long history of decentralized organizing, which is why they were able to do this. Like, you know, no one else has come close to what they do, and no one in this country until us had managed to do this kind of decentralized organizing that I'm aware of. There's a long history of failures of doing it in this country, and I think we're the first ones to succeed. So so he took me around the town. This is their first office. You can see their first wireless antenna on top of the building there. And I had a nice barbecue at his farm. Yeah, there's a farm there. And it's a big difference between GUIFI and us is that we're purely city, and they're almost all rural. So they have an advantage where they can lay fiber in people's farmland because there's no one telling them not to. The farmers can just dig it up. They have the tools themselves to dig it up. And so they're mostly fiber now. And yeah, and almost entirely rural. Like, I didn't notice them much at all in Barcelona when I was there. That's the nearest city. But yeah, they're spread way out in all the farms in the countryside. And yeah, so we're one of the. He's very impressed that we could do this in a city. So we figured that out ourselves, how to do it in a city. That's Ramon and me after the barbecue and a few drinks. So yeah, there's this board election coming up, which everyone's excited about. And the board, really, we do the minimal amount, the board, and it's weird to see everyone excited about getting on the board, and because on the board, we didn't make any decisions at all other than to approve spending. Like, we never blocked anything, because even to get to that stage, it's been through so many filters and so much decision making that by the time a contract or whatever had appeared for the board, then it was okay. It's already been the decisions have already been made. So the board, I'd say 90% of what I've done on the board in the past, was it 3 or 4 years, is in the past 2 weeks of organizing the election. So that's, I think, what you can look forward to on the board, is organizing the next election. So we have to have it because it's a legal requirement of a non-profit. You have to have a board and have to meet once a year, and they've got to make sure that we follow the bylaws of the organization. And to me, the main thing is, we make sure that the things we're doing are in keeping with our mission. And that's, to me, that's the limit of what the board should be doing. And that's just my opinion, that if other people get on the board, this could change. I hope not, but it could change. This is my personal list of worries about us growing. We're still growing really fast. And my biggest worry is that non-profits in this country are so dysfunctional, and and it's so easy to follow that path, to become an organization that spends all of its money on administrative costs. Like there's one that spends 68% of their revenue on administrative costs. Like I want us to spend as much as possible on just doing installs and maintaining the network. Last year we got up to 17%, according to our bookkeeper here, and and about, I think the biggest chunk of that was bank expenses like Stripe and yeah, so it was mainly to do with banking. But yeah, I'd like to get that lower. So, and the other unusual thing for a non-profit, most non-profits are grant-driven, most non-profits I know of. And we're basically self-funded. We've got grants, but that's not the reason we're still around. It's because we've figured out how to fund ourselves through individual donations. Yeah, and like awful things can happen in non-profits where board members get paid huge salaries and stuff. Like, I don't get paid a cent from the Mesh, and that's the way it should stay. Like, board members should get nothing. and the board so far has agreed that, that board members can't get paid, even if we have employees. Yeah, and we should maintain this focus on installs and maintaining the network. And the other thing that happens in non-profits is the internal politics, weird power structures, and long lists of rules about what you do. And what I've found whenever you see a list of rules, it's because there was one bad actor and they had to make a list of rules to exclude that one bad actor. But yeah, I'd like to avoid all of that kind of horrible, degenerative non-profit things. Yeah, we've got 2 revenue models now. The install payment page was our first breakthrough. We got down to, I think it was under $1,000 in our bank account at one stage. Like we were like weeks from going bankrupt. And it was around that time we came up with a pay page with an opt-out donation button, and we made sure every install paid the install fee, and that way we weren't losing money on each install, and then we were getting the $20 subscriptions, so that saved us, and that page is basically why we still exist. And the other thing that's happened this year is Grand Street, where we are now, which is a HPD building. I'll talk about that on the next slide, but we did a contract with them and went through a lot of negotiations to get that right, and we get $10 a month from each apartment, and we got outside contractors to do a lot of the work, and we actually came in under on that, so yeah, we spent less than we bid.
I have a question. If if a building, like, you know, decides to sign on with Mesh and everything like that, it's $10 a month per apartment in regards to internet?
Grand Street was completely different. It's the second model here. It's because it was a fiber install. And there's a lot. I could do a whole presentation about Grand Street.
And plus, they gave you the space too, which is a totally different scenario.
It's a very different thing here. But anyway, it was a huge success what we've done here, and we can copy this to other HPD buildings. It's actually easier now with the new regulations because HPD buildings have to supply internet. So an organization like us is perfect for them. And I speak to every week or two. I get a different HPD management company calling me up, asking about that. So we have these two models now, and the Grand Street one, we can just keep copying that amongst all these HPD buildings, which there's just thousands in the city. So I think that's our biggest chance for expansion. You probably heard of NYCHA, New York City Housing Association. We've done a huge amount of negotiations with them, and it's really slow. And the people that work there are really nice, and they're as frustrated as we are with the bureaucracy. But they will never get any money from NYCHA. They don't have money to pay us for anything. And yeah, and it's just ridiculously. It took us a year of negotiation for Vernon and 2 weeks to do the install. It's just a ridiculous amount of ratio of bureaucracy to.
HPD? What is HPD stand for?
Oh yeah, and the city has two organizations for affordable housing. It's HPD and NYCHA. HPD gets independent management companies to look after the buildings, whereas NYCHA is centralized. And HPD works better than NYCHA as far as we're concerned. So HPD can pay for the installs, and they're quicker to deal with. The disadvantage is there's maybe 50 different management companies you have to deal with. So yeah, so that's there's a lot to be said about that. I might answer questions on that later. A lot of people wondering how to participate, and they think there's some hidden system of participating, whereas it's all out there. All you've got to do is join the install team. You can make presentations like this one. You've got to join our Slack. That's not optional. We just do everything on Slack. And if you've got a project, you can make your own channel in Slack and try and get people interested in your project. And if you want to do things you see that I'm doing, please tell me, and I desperately want to delegate some of the stuff I do. So there's no barrier to participating in anything other than getting people interested and building up trust. I'm doing way too much, and I really want to cut down what I'm doing. Like, I'm still doing installs. Like, after 8 years, I've done over 20 installs this year. I'm still doing lots of support, and these management calls with the building management take up a lot of my time. Project management, just general planning. I'm still organizing the meetups too. Jillian was doing that for a while, but I think she has health problems. Yeah, I was doing Twitter. I just stopped doing Twitter now, and I do bits of coding when things fall apart. So yeah, and the other question about how are decisions made, this comes up a bit, and to me it's obvious that it happens in Slack, but I think because it's so drawn out and there's so many channels that people think there's some other thing going on, but if you get in there and you can follow the history, these Slack discussions go back years of people trying to decide what to do and just eventually arriving on consensus. So like, there's some things, a lot of the hubs I've got no idea how they happened, other than that it's a channel for them, and I know that things went on in there. I like the Harlem hubs, which Rob has been doing. He's been doing an amazing job on organizing that. There's the Siklu point-to-point, which Daniel organized, and that went on for ages. We switched vendors on that because it didn't arrive, the things we ordered. But all of this is in the history in Slack if you want to see how the decision process went on. And with the Grand Street Guild, I had my first meeting here over 4 years ago, 2018. It took 3 years before we actually got the project going. And yeah, there's a really long history there you can delve into. And the other thing, the third thing here is that we have this culture which I wrote a thing in the docs about it. This is just a description of how I see us working, and it's not prescriptive, it's just the way it turned out. And yeah, we work on a system of trust. You get to know people, so then they get the passwords to different things, and we know they're not going to mess it up. And so yeah, you just get in there and chat with different people and show that, or learn how to do things. Like we'll teach you how to do different things, and you just gradually get to do more and get more involved. Yeah, because there's no structure, that people think there might be an implicit hierarchy, and there isn't really. You'll see that I do more than most, but that's not out of choice. I'm just trying to fill in things that we need to do, and if I can get other people to do them, I will. The other bizarre thing is that most of us are softly spoken. It's this weird thing. Clayton from Silicon Harlem came to a presentation once and pointed it out, and I've noticed it ever since. Like, we don't really have people that yell and jump up and down that much. But, and the other thing is we try to avoid any unnecessary jargon and nerdiness. And we're very much into teaching people how to use technology. So that's all on the in the docs if you want to read that little bit I wrote on culture. Thank you. And next up will be Zach. Are you ready with your presentation?
All right. So going counter to what Brian just said about no jargon, there will be a little bit of jargon in this presentation. So, okay, so the disclaimer on this presentation. I don't usually like disclaimers, but I thought it'd be kind of fun. You're not expected to understand all of this, but it could be interesting. So there is some jargon, but it is actually a medium high-level presentation. This stuff takes years to understand, and so this is kind of a presentation about what I found over the last many years about this and what we can do with it at NYC Mesh. There's a lot of bugs in this code that I didn't write, so if you try to do this yourself, your mileage may vary. We might also want to have a technical breakout at some point, like a hackathon, to go deeper into this stuff, because it is actually really interesting if you're interested in it, but there's a lot more to it than what I'll show. And that said, even though there's tons of bugs in this code, the people who wrote this code are really awesome, and they're very helpful, so thumbs up to them. Okay, so a bit of a history. NYC Mesh has gone over the last many years from being very small and having a first node up to 22 nodes. We built Supernode 1, Supernode 2, 3. We had COVID. And so here's just a timeline of some things that we've done in the past couple of years. The number of nodes, if you take the same kind of timeline and you put a very boring text below it, and you say, well, the number of nodes is sort of growing It's sort of doubling every year, if you will, approximately. And we're somewhere around 1,200 right now, maybe 13, I don't know. Anyway, active nodes that are online routers, not necessarily people. And if you look just over some history, we have different types of history of how much bandwidth we've used to the internet. We've used somewhere around 70 to 100 megabits 5 years ago, and we're touching around 2.5 gigabits right now. We'll probably be over 3 by the end of the year. So we're actually growing quite a bit in our bandwidth. As well, an interesting thing is the number of open connections. So like if you open Google, that's maybe one connection, but Google actually opens like 5 pages within Google for images and stuff like that. So the number of active open connections simultaneously, kind of at a peak hour of the day in the mesh, is somewhere around 130,000 connections. So that's just various pages that are being opened and stuff that's being loaded. And that's kind of an interesting number for a moment. I'll tell you in a second, you'll see. So holding that in your mind, and then looking, what does NYC Mesh Network look like? Well, we have all these hubs, we have these supernodes, and we have all these tiny little hubs and nodes that are in between. This is not to scale nor representative, but there's these big things, there's these small things, and they're kind of all tied together. So most of these lines are accurate. But there's this thing at the top, and that's the thing we're going to zoom into today. And we usually don't zoom into that very much, so that's kind of why we're going to look into that more. And well, what does it look like inside? Unfortunately, sadly, it's pretty basic. It's not really anything that interesting. It's a couple of computers hooked together, and then internet goes into it. Why? We haven't really needed more than that up to now, because we've really only had a couple supernodes. It's been sufficient. And really, there's only 2 computers in there that actually do anything. One is this Supernode 1 router A, which is about 18 years old. It's ready to go to college. And the other one, we should really put it away out of the house. And the next one is the Supernode 3 Edge 2, which is, it's a very, it's fine, but it's not great. And so this does pretty much, like, if either of these go down, then we're kind of screwed. Like, we can do something to recover, but it's not great. And if you look at the internet connections we have that go into these, you could shake your hand about whether this is exactly correct or not. But we have 2 40 gigabit connections. We have a 10 gig coming very soon. We have another 1 gig. We have 3 to 4 upstream peers. We have about 3 to 4 upstream internet providers, including like NYC Board of Elections, which is really nice of them. And we have about 50 peers, nearly 100 gigabits of transit capability that we're not actually tapping into, right? And if we go into NYX, we'll pretty much double our peer count, which will be interesting later in the presentation as well. So some numbers. If you look at our public internet sources on the right here, this is the mix of, if you were to go to a website, through which provider would, who donates transit to Mesh, who would it go through? And we're fairly evenly mixed at the moment. This is just one view. This is Supernode 1. Other nodes would have a different mix. Other supernodes have a different mix. And normalizing that is kind of important in the future. But you can see it changes daily. The mix is continuously changing. So what drives our need for growth or change in this area? The number of connections. I said it's around 130,000. We can't do more than 65,000 connections per router. And so we're nearly at the top of what we can do in terms of number of open things simultaneously on the mesh, which hasn't bit us yet, but it will soon. We also need to move to a different type of NAT, which I'll talk about more later, but we're kind of restricted to a small number of IP addresses that people access the internet through, which is really silly because we have a lot of IP addresses. And spreading out this number of addresses will change the number of connections. It'll change the view that people have of the internet, the stability, and a bunch of other things. There's a lot of risk. As I mentioned, there's some poor quality or old hardware on our edge. The configurations are not really reproducible. Like, if you give me 4 hours, I could probably build a new one, but that means there's a giant outage for 4 hours, right? And somebody has to physically go there and do something with it. No redundancy as well. And then there's this interesting thing we'll touch on later about bandwidth management, where we have these cool internet connections, but we don't really do anything intelligent to select the path that your traffic goes in or out of. And then performance, of course. Right now, even if we wanted to use more transit, we are limited to about 4 to 5 gigabits total. Good thing we're only at 3 or 2, so we're fine for today, but by the end of next year, we probably won't be fine anymore. And there are some feeling of bottlenecks within the mesh, which are more accurate. So what's a good alternate for these edge routers? Well, we could go with like a giant Cisco or Juniper router, which is over $100,000. They're huge. They're closed source, obviously. They don't do everything. A lot of these are actually pretty good edge routers, and they could do 500 gigabits or more of traffic, but they can't, some of them can't do NAT, and some of them can't do NAT the way you want. So you would have to have another router next to it to do another thing, and so you end up piling up lots of equipment that doesn't really make a lot of sense. And again, it's real dollars that would be better spent on buying antennas and stuff like that, right? There's some projects like the BSD router project, which is kind of fun. For a couple $1,000s, we could build a BSD router that would do about 8 gigabits. It's not really pushing the envelope of what we can do. It doesn't get us much farther down the road. And there's a couple alternates to this, but these guys are pretty nice. And then there's the thing I'll talk about, the FDIO VPP DPDK, which we'll unpack that in a second. And for a little bit higher price, we could build a router that will do somewhere between 40 and 100 gigabits, depending on how we build it. And that's the thing I've been working on for a couple of years. So what is this VPP DPDK? It means it's a couple programs. One is called vector packet processing, which it processes packets in vectors, okay? Whatever that means. And then there's DPDK, which is this library written by Intel that basically communicates with the network cards and lets you do all of this. And so what is this combo? It's a program that directly communicates with the network card. It sits there and there's just an application that runs and it pulls for packets off of the card. So it's like reading them off the wire continuously, sort of. And it receives them in these large chunks of memory called vectors. And then it processes them in a graph like over here. So you say, well, okay, this is a packet. You remove the different pieces. We'll see a little bit of this later. And then you figure out what kind of a packet it is. And where it should go, you look it up, and then you send the packet there. Example features, you could do about 14 million packets per second per core. So that's kind of, in the ideal world, right? Millions of routes, thousands of routing contexts. You could do special NAT variants we'll talk about. VLAN gymnastics, so you can kind of like switch packets around in arbitrary ways. And it also includes crazy fast VPN endpoints, which is really something interesting for us. It's like a pain point sometimes in our mesh. But what about that $100,000 box? Well, VPP is actually donated technology to the open source world from Cisco. The ASR 9000 platform basically is VPP, and it is in these line cards. Each one of these is kind of a VPP engine. So basically, it's like the open source implementation, literally copying the thing that Cisco donated to the open source and being done by a lot of people. So we're done, right? That's like we're done, everything works, we should just move on. Not quite. That was a great joke, right? Everyone laughed. Everyone laughed in the room for people on the mesh or on the internet. So this project, VPP, started around 2016. It worked, but only supported a few network cards, and it had a lot of problems. And then in 2018, which is when I started getting interested, there was a plugin called Tap Inject, which allowed you to basically use it as a router rather than just kind of arbitrarily mangling packets on the wire. So I spent about 6 months on and off on the mailing list trying to talk to contributors and trying to compile the thing. And by 2019, Tap Inject was broken. It no longer functioned with their mainline code, which was pretty sad. And then, this is a very well-known thing that this doesn't work anymore. And then they added CGNAT, and they made it better, which is kind of something we really need. So that was great, but there wasn't any way to use it, which is unfortunate. And there wasn't really any changes in 2020. Sometimes VPP is used for Kubernetes if you have like a really giant Kubernetes system. So a lot of work was done in there. So the big problem is there's no nice way to control the routes that go into VPP. In 2021, there was still COVID. And this guy, was there still COVID? Or Yeah, that was still COVID. And this guy, Pim van Pel, he's Swiss, began working on a project called the Linux Control Plane Next Generation, LCpng. And this makes a connection between bird or FRR in Linux and the VPP routing table. So this is the missing component that everyone wanted to have. He runs a small ISP and he wanted to use this. And so his target was about 10 gigabits per second with this plugin still functioning. He released it in Q4 last year. It had a lot of bugs. I compiled it. It didn't work. There were a lot of problems with it, but for him, it worked for his use case, right? And then in the beginning of this year, it was rewritten sort of again. A lot of major bugs were fixed, which, when you start using it in production, you see there's a lot of bugs. He presented at NANOG, and it actually worked. It compiled, it works. However, this is a complicated project, so a lot of the other libraries didn't work at that time, so something was always missing, right? And so in the last few months, what I've done is I've started over, I changed to new hardware, I changed to new cards, new operating system, just everything from scratch, tried to build it the way they built it, and I got it working, right? So finally, this year, we can actually use it and it functions. Here's my test rig that I'm using. I have one server that's an Intel 20-core server with dual 100 gig Ethernets on it. And if you just loop those together, you can get 76 gigabits of traffic between card A and card B. Now, why 76 is limited by PCIe and memory bandwidth. So this is all that computer can do. I plugged it into a Juniper switch, exactly the same kind that we're going to use at Supernode 10, with 40 gigabit. I put it into a VLAN, put it into a bond with 10 gig, put 10 gig over into the server, and then pin that to one socket in the server, which all the way through the route, through the switch, you can get full 40 gigabit. And then the part we're testing is all the way over to the right side, right? The reason that there's a lot of 10 gigs here instead of 40 gigs is because of all these problems with these different network cards. This is the card that works, right? So we need to do something there, and we have to figure out what to do about that to make it performant. What are the results? So there's results, and basically it will go full speed, right? So the iMix, there's a couple tests here. I'll talk about them. The first one's called iMix. This is a test that a lot of people have different opinions about. It's kind of a standard test, but it doesn't really do anything useful. It's just, let's do a mix of this size and that size and this size request. And it's a common thing people do, but it's not representative of anything. So you can do about 14 gigabits and 37 million packets per second with a 30 microsecond latency. So it's pretty good. DNS packets are interesting because if you ever have a DDoS, DNS is usually the thing that's used for DDoSing you, right? So if you have a denial of service attack. So the ratio of data in to data out is, data out to data in is 1.2 to 1. So you make a DNS request and you get back a packet that's very similarly sized, slightly smaller, and we could do about 18 gigabits. So we basically can handle an 18 gigabit DDoS attack with this infrastructure if we wanted to. The limit was actually, interestingly enough, the test box. The test box had 20 cores. I mean, the test server, the left-hand side, the Intel 20 core. So even though that server had 20 cores and the VPP server had only 8 cores, the VPP server was faster than the test box. Right? So it's kind of interesting to see that it is very efficient.
Test box generates the traffic?
Yeah, the traffic generator, exactly, yeah. I probably should have worded that better, yeah. The other test, there's a data center mix, which is 3 out to 1 in, and then a web traffic mix, like if people were downloading streaming movies or whatever people do, looking at Twitter or whatever, or Mastodon, sorry. And then you can get about 37, 38 gigabits and about 5 to 10 million packets per second. So this is actually really good. If you look at it, our Supernode 3 router right now, the total end-to-end latency of Supernode 3 is about 1 millisecond. So this is way lower. There's a couple other, it might creep up a little bit depending how many things you have plugged in, but it is actually a big improvement. So we basically crossed off performance. We figured out the performance part of this puzzle. We crossed off risk because this is all new hardware. It would have to be new hardware. This doesn't work with anything we have already, right? So the next thing we can concentrate on is the number of connections and the CG-NAT problem. Well, VPP does CG-NAT. Well, firstly, what is CG-NAT? It's called Carrier Grade NAT, and it's a way for ISPs like T-Mobile does this and Spectrum does this, where they take your inside IP address, which is like on your cable modem, and they compress it into a limited port range on the outside. And so you can, for example, if you had this IP on your cable modem, this is like an example, somewhere in Spectrum they would have an IP like this, and you would go between these ports only, right, for your outbound traffic when you connect to somebody like Google or Twitter or whatever, right? It has a lot of, well, okay, so why bother even thinking about this? Yeah.
So that's different from regular NAT just in that you're using a specific range.
Yeah, it's different. He asked is it different from regular NAT because it's using a specific range? The answer is yes. Regular NAT, you basically choose an open port, a random open port. And so this is, it's more memory intensive because you have a table for every IP, but you also, it's easier to find the IP that's available, or I mean the port that's available. So it's a little bit more efficient, but largely it's used for things like the purpose of this is for law enforcement, which we're not interested in doing anything with that unless they ask us. Please don't. The idea is that you can look at this port and you can say who did a thing on that, and you can look back inside, right?
Right, there's traceability there.
Yeah. So we don't have that need, but
Where's the microphone?
yeah.
It's green. Green? Okay, I don't have it turned up. Now it's fine.
Okay.
Yes.
So then, yeah, how does this differ? Like, what's the benefit of this to us, right?
Yeah. In its pure form, the benefit would not be that great, right? What we do need to do is somehow find a way to distribute people over more than one address on the outside, right? And so what do we need to do, right? We need to distribute people through more than one IP, right? So we can get more than 65 connections, 65K connections. This is redundant. But if we do that now, the way we have it, if we were to just do that on our existing equipment, for any one connection you open, it might be on one IP or it might be on another IP. And so websites won't function properly. There's a lot of problems with that.
Right, you need to do the bookkeeping to keep track of which, yeah.
Exactly. You need to find a way to pin people to one address or another address. And up till now, there's a cool thing I'll talk about in a second, but up till now, you could either do the random thing, or you could restrict people to one IP, or you can make thousands of fancy rules that say, for that person, go here. For the second person, also go there. For the third person, also go here. For the fifth person, go there. And you can basically map it out manually. Or you can do something really creative and do CG-NAT or something else. So that's kind of why we're going down this road. So the benefits of CG-NAT, as I mentioned, there's faster mapping. It's application-based, so it's kind of threaded. You can spread users over many addresses, and it's kind of done in parallel because you don't depend on, like, people go through different streams of routers in order to, you can go through different streams to be able to do a CG-NAT. But the big downsides is that because there's this port range for every user, you're restricted to no more than NAT connections, right? So if you have 100 tabs open on your browser, it's not going to work very well, right? And so this is a problem for people because they're going to probably do that, and it's not going to work, and they're going to complain, right? There's also less privacy because of the CG-NAT is basically made for law enforcement, right? And another big issue is because you have this port range for everybody, you have to have however many nodes and IPs you have in the mesh times the number of ports, which means we have to have a huge chunk of addresses that are not well used. So this is not even really great for us. People complain about things like, my games didn't work, because of the port range problems and all this this is a common problem. It's also quite hard to find a good implementation, especially an open one. So an example of this, VPP can do CG-NAT. So if you look on the left, you'll have a very number of nodes, and they'll kind of all map to their own little port range on every different IP address. But recently, as in a few months ago, there was a feature which isn't named, but it's called, I'm calling it for the purpose of today, sticky NAT, which lets you do regular NAT, but it hashes IPs over the internal IPs over a fixed number of external IPs. So basically, everyone can do 65K connections, but it limits you to only do it out of your assigned IP address. But you're not doing it manually. You can have as many internal IPs as you want. So this is what we need. This came out this year. So this is a thing that will really make a big difference for us. It solves the privacy concern. It solves the port limit. And there's no number of outside IPs that are required. So this, basically, we're not doing CGNAT. We're doing fancy regular NAT, right? But VPP does this, right? So this is not something you can do with sort of a boring router. And somebody thought this was a good idea, and they committed the code, so it works. The last thing we need to really worry about, the problem we're trying to solve, is bandwidth management. And this is a complicated thing. People spend their entire careers trying to figure this out. But we have a much simpler version of this problem. It's just we have to do something about it, right? We can't just do nothing. We have to do something, right? And so, for example, the problem is if you have one router like we do at either of our supernodes right now, if Internet 1 is much larger than Internet 2, and you have 2 internet connections, right, the router will just flow out everything based on its best path, right? And so what you don't want to do is say, I want everything to go through Internet 1 because it's faster. You want some things to go through Internet 2 because you need to use it a little bit, but not everything. And so you have to figure out how to easily flow some traffic through one and some traffic through another. But if you have 2 routers, even at the same location, and let's say you want to do redundancy, you want to allow either router to die, and you put 2 of them and you plug each internet into each one, some odd things happen. One odd thing is that one side might go underused or not even used at all, depending on how your traffic arrives at the router, right? So some people may always be going out Internet 2, some people may always be going out Internet 1, and some people might go out Internet 1 today, but might go out of Internet 2 tomorrow, depending on how their traffic arrived at the supernode. It also will only exit, so if you arrive traffic at router 1, or the green one, or let's say router 2, which is labeled 1, the red one on the right side, I did a poor diagram here, then you might have no way to go out of router 1, right? And then there's another odd thing, which I saw many years ago, and it can happen today, is that if Internet 2 has slightly more routes than Internet 1, and it has different ways of getting to, let's say, Netflix than router 1 may always give the traffic to router 2, and then it exits. So it depends on the view of the internet. You may or may not go out of router 1 or 2. And so there's a lot of nuance and issues with this, and it's a huge pain if you have more than 2 connections even. So what we need is another layer of aggregation. And if you look at really large internet organizations, they have what are called aggregation routers, and they have edge routers. And part of the reason they do this is because they need to have a way to exit traffic through any internet connection they choose and make the selection somewhere else. And so we need to make an aggregation router as well. And we can do all of this function within the same, I think, VPP instance. And so this is not something that we have to buy a whole bunch of different chassis, a bunch of boxes for. We can do it kind of in one system. And that means that we can choose, using good selection methods, maybe one person goes to Netflix through Internet 1, maybe somebody else goes to Netflix through Internet 2, and we can distribute the load, various ways using, arbitrary selections like changes on the router, rather than having to physically recable it, or rather than using randomness, right? So it's kind of a cool thing. And then when you talk about the CGNAT and how it comes in, what we do today is we just push everything through one direction and we NAT everything. But IPv6 and even public IPs don't get NATed. And so we have this complicated thing where there's different rules that say, if this address is like this, then do this. If it's like that, do the different thing. And instead what we can do is we can make this NAT system we talked about very dumb and redundant. And we could put it over in the corner, and then we just push traffic to it that gets NATed, and then it comes back into the main network and goes out. And so we can make a very normal way of doing this that is redundant, balanced, fast, and future-proof. Okay? So the next steps for this are we need to order some new Dell servers, which I've been talking to Jason about, and I'm a little bit behind in actually doing it. We need to order some new NICs, some new network cards. There's a little bit of an interesting thing here because I really wanted to get us to 100 gigabits, but those cards VPP is just such a pain with that. I think if we do 40 gigabits, we'll be good for many years, which is kind of cool. The sticky NAT that I talked about, it works, but it's a little bit buggy, so it's another thing that has fun bugs in it that need to be worked out. And there's other challenges, like multiple routing tables. I mentioned these different things can be in the same VPP system. Right now, the control plane thing that Pim wrote does not work with multiple routing tables. So there's some other question marks there. And there was a question on the mailing list recently about whether you can do NAT and routing on the same instance or not. So these are tests. And then, of course, because I've mentioned a lot of this is kind of edgy, we need a backup router of some sort, right? So we need something that sits on the side that has a little tiny bit of traffic that can flow, like it can make the people in the mesh happy while the big one goes down because it broke for some reason, right? And lastly, in the line of things breaking, like VPP is sort of stateless, and you can't really, it doesn't really save the configuration, so it's kind of scary. And so that same guy, Pim, is writing something that works with the configuration with a live VPP instance. So it's kind of interesting it's still fairly raw, right? So challenges aside, I think it's still worth it. This is a 10x capability for us, and I think even though it comes out slowly, I think it's worth it because we're not at the limit yet, but we should really we should look for the limit coming up. And so big thanks to Cisco, DPDK, FDIO, Intel, and the people, especially Pim, who did a really good job, and a couple of sponsors who donated some of this hardware that we're testing with. So pretty cool. Before questions, some bonus material. If any of you are interested, I mentioned that it's kind of polling, so I apologize if people don't understand all of this right here, but you can see that this 8.01 means that this process is using 8 CPUs of work, and it is basically just sitting there 100% CPU, like, do you have a packet, do you have a packet, do you have a packet, do you have a packet? And it's just doing it on all of the CPUs simultaneously. So it's kind of interesting. And actually, I can do a live thing here, but it's passing, this is a bandwidth test in T-Rex application, so it's doing it. And we can go into this more if anyone's interested, but you can completely trace, there's that packet graph that I showed earlier, you can completely trace every packet that goes through and see, like debug trace. I mean, what happened? Well, it came in this card, and then it looks like this, and then it went through the bond and went through the Ethernet, and it decodes all the things and makes a decision down here about what to do with the packet. So it's actually really interesting to dig into how it's going through and any kind of, to see what happens there. So, yeah, thanks. Any questions? Yeah.
Yep. Can you hear me? So you were talking about redundancy, and I think that relates to uptime and failover and things like that. And then you also talked about running on the exact same piece of hardware at the same time for multiple components, right? So I guess I would see this as, first there's multiple supernodes, right? So exiting traffic from one or another, but let's just point at one supernode for now and not try to think of complicated things like connecting them into each other, right? So are you talking about now having 2 slices of physical hardware inside of there and both of them splitting that load? So if one fails over, who cares if it loses state, and the other one just picks up from that point? And then if that one fails over, who cares, because in the background you fix the other one and then that comes back, that type of a thing?
Yeah, sort of. So let's say if we go back here. So looking at Supernode 10, for example, right now we only have one connection. We're about to have another. And across this one, we're probably going to have multiple upstreams. And we're probably going to move this one over there. So we're probably going to have, I think late 2023, we're going to have 6 internet connections at Supernode 10, right? So, or 6 upstreams, right? So we don't have to put them all onto one router. We can put 2 or 3 here and 4 or 5 there, or whatever. We can mix them up. And the ones that have more performance, we can put them onto a faster one. The ones that have lower performance, put them on an appropriately sized system, right? So what that would do is if one goes down, we can just use the other ones, as if there was an outage from the provider instead, right? So if we can do redundancy, if it's only thousands of dollars for us to do redundancy in there, because it is critical infrastructure, or it should be critical infrastructure, we might as well do it, right? And I think in a table, in a picture like this one, we can have multiple aggregation routers that actually load balance, and we can have multiple switches that are, parallel, right? NAT engines are sort of, I'll put a big star here, they're sort of stateless, so we can kind of be okay with that and have multiple of them, right? And then these routers are just, it's only for that path. So if you lose any one of these things, there's another one that does the same thing. So it'd be nice, if we can achieve this, that'd be great, right? If you only have one connection, with the way things are today and with the way all of our providers are, for example, we don't get 2 connections from them. It's not like a critical thing for them to do, right? So we can't plug it into 2 routers. It's going to be one or the other. And we can do heroic things to make it happen, but it might not be worth it, right? Yeah.
And so then this probably steps a little bit out of the content of the presentation, but as you exit that space and you go into distribution networks, right? So I don't know if that's like redundant in any capacity at all whatsoever, or if there's just like sectors that are only the sectors, right? So we might have this great redundant infrastructure that's, inside our peering exchange, but then not our transition layer as it gets outside.
Yeah. Doing it with no context about why we're doing it would be dumb, right? But for example, Supernode 3 has, 7 or 8 antennas off of it. So, they're not redundant, but they go into this web of the mesh, right? And so if we, most of our Supernodes, except for Supernode 10, which is brand new, have 3 to 8 antennas, right? And so even if we lose one, well, the traffic will flow back here and then back out. The important thing is that these things are designed to fail, and we're building them purposefully in a giant web, and we're not doing that with our Supernodes right now. And we should, so that stuff down there, which is well constructed in terms of redundancy, if you will, let's just assume it is for now, that's an opinion, then, if the Supernode goes down, then none of that matters, right? It doesn't function anymore, yeah.
So now speaking a little more to the rules inside of it for determining exit traffic, right? So like at my place, I have dual WAN, right? And I spend a little bit of time picking out going one way or another. Yeah. Every once in a while when I leave the house and it says, oh, I put a lot of stuff over into Spectrum right now. Let's put some stuff into Mesh. Yeah. All of my things on my Apple TV are very upset, right? I have to exit every application. I have to reopen them because like it tries to keep those active sockets going to a spot that it doesn't have a route against. Yeah. So, what's that? You took what? Oh, you have the same setup? Yeah, the same setup. Yeah. So all of us are terrible at doing this. Yeah, so how are you better at doing this?
Yeah, so this is different because we're using, when we talk about internet connections, I'm assuming that there's BGP between all of these. And so there's an IP address space that's shared among all of this. And let's say, for example, let's do something really trivial. NAT engine 1 in the back here might have like our 208 address space. And that engine in the front might have a 23 dot address space. These are public addresses. And so we might lose one, but, if we lose a connection, there's different things that will fail different ways, right? So your example of the internet failing or switching from mesh to Spectrum, that would be the equivalent of losing one of these routers or one of these upstreams. That doesn't make any difference to us. Your path to internet is changing all the time when you're at one of these edge nodes like this. And so you would see no difference. I've done this live on Supernode 1, and we shift people's traffic a different direction, and you'll never know, right? What you might notice is if we lose an entire NAT engine, you might notice it for a moment, but this is like a hard failure that is recoverable, right? These other ones are soft failures that are transient. You won't notice them, right? They'll just occur, and then sometime later it'll come back. This is normal. So the idea is put as much as you can into normal transient things that don't make any difference to anybody. The path changed, traffic is still flowing, no one notices, and then you shouldn't have any problems. So this accounts for that, is what I'm saying.
Can you speak a little bit more into the VPN? So you talked about how that's like, it's much better, right? It's super good VPN or something. What was your descriptive word inside of it?
Yeah, so VPP is this C C++ application. And these different nodes are, encapsulating and decapsulating. So if you look here, this is like coming in from the PCI. This is basically removing the bonded interface. This is removing the Ethernet pack frame. It's removing the IPv4 frame, right? And so what you can do is people make a VPN decapsulator node. And so somebody's made one for IPsec, someone's made one for WireGuard, someone's made one for a whole bunch of different things, GRE, for example. And so the super good part of it is that because it's not running in the kernel, and because it's not going through Linux, it's going through the application, it's just treated as a node in this graph. So basically, it would have similar performance to all the other things. Like it can be parallel, multi-core, as fast as you can go, right? So people are seeing, like there was an article recently, someone did, was it 800 gigabits of IPsec encrypted traffic between two VPP instances? It's like insane, or 600 I think it was. It was an example set up at, I think, Cisco, and like it just does it, right? So it's not a different VPN, it's not something new, it's just the fact that they go through this pattern allows you to decrypt packets, in this very fast way.
Okay, yeah, I guess I was asking because there is, like with expansion, right, where we don't have, we can run fiber, we can do these microwave links or whatever, right? But like eventually it seems like Harlem expansion, that's a VPN thing, right?
Yep.
And there's like, I forget the new name of the spot that's,
Yeah.
But there's another VPN spot that's an exit from that. So I assume more traffic will show up at supernodes that are exiting through that location, right?
Exactly, and so that's a one reason why it's worth calling out is that our VPNs right now that suffer a little bit. I mean, if we don't have to do a VPN, we shouldn't, right? But if we do a VPN, we can begin to move to this style, and those existing technologies should be improvable, right?
Back to your high-level block diagram network architecture at the beginning, there was the link between the supernodes for the connectivity that went over the top.
Yep.
Is that intended to be a VPN link between the two? Or what is that?
Yeah, these are actually VPNs right now.
Okay,
Yeah.
cool.
Yeah.
That's what I figured.
And we, part of the unwinding of the legacy pieces is today we have to have those. In theory, we don't have to because we actually have paths between all of our supernodes across the mesh. But because we only have one router on the outside, and because it does NAT, and because of the way we do our transit, today we do need to have these in order to exit the traffic successfully. Like if you have a supernode 1 IP that shows up at supernode 3, we have to somehow transport it back to supernode 1 to exit.